This is problem 3-72.m. It's on page 168. Figure P372 shows a load being applied to an inner cylindrical member that is initially 0.12 millimeters longer than a second concentric hollow pipe. What would be the stress in both members if a total load of 350 kilonewtons is applied? So please go to page 168 so you can see the figure. I want to discuss it initially. That 0.12 millimeters, you really need to get a sense of scale here. The overall height of this system is 1.65 meters. Now that's, let's see, if we move the decimal place over 3, that's 1,650 millimeters. Now that, by comparison to 0.12 millimeters, is like trying to compare $1,650 to 12 cents. I mean, there's really no comparison. There's a huge difference in the size of these things. So there's not a significant difference, is my point. There's not a significant difference between the height of the cylinder inside and the pipe outside. It's a very small difference. Now, it is possible that the cylinder could support all of the 350 kilonewton load. We don't know yet. If the cylinder doesn't compress more than 0.12 millimeters, well then it will take all of the load. So we need to figure that out first. So the initial condition before the load is applied is what's shown there. And we're supposed to find the amount of stress in the aluminum, which is the cylinder, and the stress in the steel, which is the pipe. Okay? All right, now, one thing to note, I went ahead and converted the initial deformation of the aluminum from 0.12 millimeters to 0.3012 meters. Again, that makes it clear how much difference there is, because the length is 1.65 meters, and you can see the difference between these two. Let's see, 2 more zeros before we get to the scale of the deflection. Anyway, some stuff we'll need along the way. We'll need the area of the cylinder, so I went ahead and grabbed that. Pi d squared over 4. And the cylinder is 0.14 meters in diameter. Plug all that in your calculator. This comes out to 15,400 millimeters squared after you convert it, of course. You got to multiply by a million. What you get from here, you multiply by a million, you'll have millimeters squared. The area of the pipe is actually easier to get. The area of the pipe, you might think, well, pi d squared over 4 minus pi d squared over 4, where 1d is the outside diameter, the other is the inside. It's actually easier that you can just look it up. Appendix A12, the SI version, gives the cross-sectional area of this pipe as 3601 millimeters squared. Now, if we need either of these in meters squared, we can convert them easily. Now, what I did is I decided to check and say, okay, how much force do we have to apply to shrink down that cylinder so that now the load is applied to both the cylinder and the pipe? In other words, to the point where the load just finally starts being taken by the pipe as well as the cylinder. So I said, so what happens if the deflection is exactly that much? Well, deflection is force times length over area times elastic modulus. And so we can rearrange this to ask the question, how much force do we need to apply in order to deform a given cross-sectional area, elastic modulus, and length of material by a certain amount? Okay, so that's what I'm trying to find out here. Well, the deformation before we get to the pipe and it starts taking load is that much. The area would just be the area of the cylinder, because again, we haven't reached the pipe yet. So that is 15,400 millimeters squared. If you look up the elastic modulus, remember the cylinder is made out of aluminum. And so the elastic modulus would be 69 gigapascals. Divide that by the initial length of the cylinder, 1.65 millimeters, and you might say, well, wait a second, it's 1.65 millimeters plus that much deflection. Okay, there's just not going to be much difference in the force. Why bother typing those extra numbers in my calculator? I didn't even bother messing with it, okay? I'm more interested in making sure that I get this right. So the reason I use millimeters squared here is because when I multiply by gigapascals, I will be left with Oh, I'm sorry, I wrote 1.65 millimeters. Sorry, 1.65 meters. The reason I wrote millimeters squared here and gigapascals here is I'll be left with kilonewtons from this. So the meters will cancel, and again, that's why I converted the deflection into meters, so it would cancel here. But anyway, that way I'll be left with kilonewtons. When you plug this in your calculator, you'll see that it's about 77 kilonewtons. Since we have a load of 350 kilonewtons, that means definitely the load will be taken by both the cylinder and the pipe. So since we've got that much done, let's move on. We don't need that anymore. We know what we're looking for there. Both the cylinder and the pipe are going to take the load. So the total force will be equal to the force in the cylinder plus the force in the pipe. Okay. Now, the equation I had up a moment ago for force is force equals deflection, AE over L. Now this equation could be applied to the cylinder and the pipe independently. In fact, I could plug in and say, well, the deflection of the cylinder times, I'm going to leave some space here for a reason, times AE over L, where all of these are talking about cylinder properties, the aluminum, plus the force in the pipe, which is the deflection of the pipe, AE over L. This is just steel, basically. These two together give me the total force because both the cylinder and the pipe are pushing up, not with equal force. Right? The force is not evenly distributed between these two. Now, further, the deflection of the aluminum is more than the deflection of the pipe because notice the deflection of the aluminum has this initial deflection built into it. So what I did is I decided, since I wanted to find out how much more the two would deflect, I wanted these two to be the same symbol. So what I decided to do was just add the 0.12 millimeters. And so now these symbols mean the same thing. Now the lengths are the same because, again, the difference in the length of the cylinder initially versus the pipe is negligible. So I'll approximate those two as the same length. The cross-sectional areas are obviously different, and of course the elastic moduli are different too because it's two different materials. But now at least this deflection, this delta that I've got, is a different delta. Let me call this one delta sub I. Okay, to talk about the initial deflection of the aluminum. And of course the aluminum is going to deflect an amount of this plus the 0.12 millimeters, its initial deflection. So I could have used delta sub I, but I thought this would make more sense. Now, we've used this so we can get rid of it, but this will allow us to solve this problem. All right. Now, since both of these lengths are the same, and by the way, we know the total force, right? That's the 350 kilonewtons. Since both these lengths are the same, I can pull them over to the left-hand side and say length times total force is equal to, and I tell you what, while we're at it, since I'm pulling these over, notice I'm going to have a product here of 0.12 millimeters times AE for the aluminum. I'm going to pull that to the left-hand side as well. So minus 0.12 millimeters, A of the aluminum, or the cylinder basically. We've already defined it, so we'll use it. And E of the aluminum. Okay, so that's just taking this piece and moving it over after multiplying both sides by the length. Anyway, that's equal to what's left, which is delta A of the cylinder times E of the aluminum plus delta A of the pipe, E of the pipe. And you notice where I'm going with this, of course, I'm going to factor out this delta. So if I factor that out, it looks like this. And that way I can divide both sides of the equation by this term here. So basically, the amount of deflection above and beyond this that the aluminum will experience, or the amount of deflection total that the steel will experience, is equal to, well, we've got this term here that will be in the numerator, LF total less 0.12 millimeters area of cylinder elastic modulus of aluminum divided by this term over here, the area of the cylinder, elastic modulus of the aluminum plus area of pipe, elastic modulus of pipe. Now we can plug in numbers because the length initially of the pipe and the aluminum, as far as I'm concerned, is 1.65 meters. The total force being applied is 350,000 newtons. And then the other terms are 0.12 millimeters for the initial deflection of the aluminum. The area of the cylinder, well, we've got that, it's right here. It's 15,400 square millimeters, and 69 gigapascals is the elastic modulus of the aluminum that the cylinder is made from. We have to be a little bit careful here because we have kilonewtons times meters here, but notice that millimeters squared times gigapascals would give us kilonewtons, and we have millimeters here. So we need a conversion factor just for this last term to give us meters. So there's 1 meter per 1,000 millimeters, and basically that'll take care of the millimeters on this initial deflection. Of course, I could have just written 0.3012 meters, but I wanted to show you that conversion and remind you to be careful about your units. You cannot add apples and oranges. It doesn't work. You have to be measuring the same thing. All right, now in the denominator, the area of the cylinder, 15,400 millimeters squared. We've got that term. Elastic modulus of the aluminum is 69 gigapascals. And we need the cross-sectional area of the pipe, 3601 millimeters squared, and the elastic modulus of the pipe. Now if you look that up, you'll find that for most alloys of steel it's 207 gigapascals or so. Okay, so we've got millimeters squared times gigapascals. This whole denominator will have units of kilonewtons, which will cancel with the kilonewtons here. Please pardon my phone, I forgot to turn it off. Okay, so anyway, the kilonewtons will cancel, and notice that we'll be left with meters. Okay, so plug all this into our calculator. What do we find? Well, the excess deflection above this initial for the aluminum, or the total amount of deflection for the pipe, is 2.489 times 10 to the negative fourth meters. Now, writing that in something a little more, a little easier to read, this means that the deflection of the pipe is about 0.25 millimeters. Okay, so I just rounded it up a bit. This is really close to 0.25 millimeters. And the deflection, of course, of the cylinder would be its initial deflection of 0.12 millimeters plus the 0.25 millimeters. Because remember, the cylinder compresses a little bit before it compresses with the pipe. Okay, so that's just 0.37 millimeters that the cylinder compresses in total. Okay, so why did I do all of that? Well, now that I've got the compression of the pipe and the cylinder, I should be able to calculate the stress. In fact, the equation for that is like this. Let's apply it to the cylinder. The stress would be the deflection of the cylinder times the elastic modulus divided by the length of the cylinder. So that's 0.37 millimeters multiplied by 69 gigapascals divided by 1650 millimeters. Now the reason I did that is so I could just get rid of the millimeters. Plug this in your calculator, you'll find that it's about 0.0155 gigapascals, which is 15.5 megapascals. So there's the stress within the cylinder, which is one of the things we wanted to find. Now we need the stress in the pipe. Well, we'll use a similar equation. The steel pipe has a stress equal to its deflection. Let's see, how did I write that? Pipe, elastic modulus of the steel over the length, and so that's just 1/4 of a millimeter. The modulus of the steel is 207 gigapascals, and then the length is 1650 millimeters. So the millimeters go away. Plug all that into your calculator. And looks like I did this one wrong. I multiplied 0.12 in my solution on accident. And I actually do have a calculator with me. It's not a very good one, but here we go. So let's see, calculator on my phone of all things, 0.25 multiplied by 207 and divided by 1650 gives me 0.031 or so. So this is about 0.031. Let's take another digit 4, and so that is, let's see, 1, 2, 3, that's 31.4 megapascals. And so which element takes the most stress? Well, it's obviously the steel. And so that's now, does that mean it's taking the most load? Not necessarily. Notice the area of the pipe is a whole lot less than the area of the cylinder, and so just because the stress is higher doesn't necessarily mean that it's taking the higher total load. We could go back, let's see, where were we? Here we go. Once we've got the deflection, we could actually go back here and calculate the force in the cylinder and the force in the pipe, but I'll leave that to you as an exercise.